Hi students, welcome back to myclass.com. Graph representation. How graph is represented in a computer memory. That is our topic in this video. So our topic graph representation. There are two ways to store graph into the computer's memory. We are following two different ways. First one is sequential representation, adjacency matrix representation. Second is linked list representation, that is adjacency list representation. First, sequential representation. In sequential representation, we are representing this as a matrix format. It is a matrix. We are representing this graph as a matrix, adjacency matrix. If there is an edge between I and j, then the value of that is 1 or 0. If there is an edge, it is 1, otherwise it is 0. It is for the undirected graph, also for directed graph. If it is a weighted graph, then if there is an edge in between I and j, the value is w, the weight of that edge. That is the representation, that is the sequential representation of graph. So if adjacent I of j equal to w, it means that there is an edge exists from vertex I to vertex j with weight w. In adjacency matrix, in an undirected graph, it will be 1 if an edge exists between I and j. So if an undirected graph in this, so this is an undirected graph with 3 vertices. Then the adjacency matrix, the order is, if here value is n equal to 3, so the order of the matrix is 3 by 3. So this is the name of the vertex ABC. So our matrix is like this, ABC, ABC. So this is our matrix with 3 by 3 order. If there is an edge between A to A, then it is 1. Here no. A to B there is an edge. A to C there is an edge. B to A also there is an edge. B to B there is no edge. B to C there is an edge. C to A there is an edge. C to B there is an edge. C to C no edge. So this is the matrix representation of our this graph. Okay, A of Ij equal to 1 if there is a path exists from Vi to Vj, otherwise it is 0. That is the concept of adjacency matrix representation. So this is the another example for undirected graph. Here 5 vertices are there, so our matrix order is 5 by 5, 5 by 5. So A, B, C, D, E, A, B, C, D, E. If there is an edge between A to A, then value here is 1. Here no loop is there, so 0. A to B there is an edge, so 1. B to C there is an edge. B to C there is an edge 1. So it is an undirected graph. So A to B there is an edge. Then AB also 1 and BA. The value in the adjacency matrix of BA also 1. Okay. So that is the value, the adjacency matrix of an undirected graph. For a directed graph, if there is an edge from A to B, then A to B equal to 1, but B to A, if there is no edge from B to A, then here it is 0. For a undirected graph, here also 1, we can make it as also 1, but for a directed graph, if there is an edge from that node to another node, then only it will be 1, otherwise it is 0. That is the difference between directed graph adjacency matrix and undirected graph adjacency matrix. Clear? So for a weighted graph, adjacency matrix for a weighted directed graph is only the difference is if there is an edge, the value of that position of that matrix is the weight itself. Okay, the weight of the edge from A to B is 4, so here it is 4. Otherwise, if it is not a weighted graph, it is the value is 1. If a weighted graph is there, then the value is the weight of that edge. That is the only difference between the directed graph and the weighted directed graph adjacency matrix. So what is the next representation? Linked list representation. Linked list representation. In linked list representation, the only difference is we are making adjacency list for each graph. Adjacency list is used in the linked list representations to store the graph into the computer's memory. It is the efficient terms of storage. Why? Because in an adjacency matrix, if there is no edge, then only we are entering 0 value to that matrix. Is it like that we are doing? So it is a wastage of memory. But in the case of adjacency list representation, there is no wastage of memory because only the edge values we are storing. For only the edge we are making adjacency list nodes. So this is the example for the undirected graph adjacency list. So how many nodes are there? Such adjacency list we are maintaining. Here 5 nodes are there. So A, B, C, D, E. 5 lists we are maintaining. So A, the first list is for to store the all the adjacency nodes of the vertex A only. Okay, so A to B, here this node represent that there is an edge between A to B. Here also this is represent that there is an edge between A to D, not B to D. Okay, so the first starting point is very important. Starting points adjacency nodes we are representing in this adjacency list. So here only 2 edges, B, D. For B also there is an edge A and there is an edge D. So AD we are making, and also C is there. So ADC. For C, B and E is there. For D, A, B, E are there. For E, D and C are there. So that is the adjacency list representation of an undirected graph. So for one edge we are representing 2 times we are representing that edge. So see here this edge and this node representation, and this is also representing the same edge because it is an undirected graph. If it is a directed graph, then the difference is if there is an edge from A to B, here only we are representing that edge. Here no edge from B to A, then there is no A value here. Okay, that is a different directed graph only. That values are we are storing in the adjacency list. Clear? So that is a linked list representation. So mainly 2 representations are the sequential representation, that is adjacency matrix representation, linked list representation, that is adjacent list representation. Hope it is clear now. Thank you for watching.